Okay, well, welcome to class. It's 1:20, time we get started. We're working on chapter 10, waves, this week, and I'm going to cover the review what we talked about on Tuesday. I'll finish off some of the topics from chapter 10, and then hopefully I'll open with an introduction to some of the chapter 11 topics, which concern tides and the way in which Earth waves of ocean energy that are transmitted around the planet or across long distances, how they're generated and how they are affected. So on Tuesday's lecture, we started talking about tides. We said this key point was that tides are transmitting energy, not water mass. And that's a little counterintuitive because we see water appearing to move. The depth of the water changes. But the water is, by and large, there are some important details that we'll cover that clarify this. But by and large, water is not moving the way it does, say, in a current. When we see tidal changes. Now, there are currents that are generated by tides, not to get that wrong, but by and large, the movement of water in waves doesn't occur. Only energy is being transmitted. We classify tides according to several characteristics. The wave size, the water depth, in particular the water depth in terms of the wave size. And we looked at friction. Most of the waves that we've talked about so far are what we call wind waves. These are waves generated by friction of wind blowing across the ocean. So the different classifications were wind waves, and we classified waves also in terms of the wavelength, the distance from peak to peak or from trough to trough of a typical wave. And in a wind wave, the wavelength, the distance from peak to peak, is somewhere between 60 and 150 meters. And the disturbing force, what creates the wave, is wind blowing over the ocean. So we'll talk a little bit about that in a second here. And then we identified some other types of waves where the disturbing force was extrinsic to the wind, had to do with the shape of the basin or disturbances in the basin. And these include seshing, seismic sea waves, also called tsunamis or tidal waves, although tidal is a little deceptive in this case. And then the tide, which is a type of wave, and we have to call it a wave because it's energy being transmitted through the ocean. And that energy, the disturbing force in this case, is the gravitational attraction of planetary bodies, particularly the moon and the sun, acting independently and together. Okay, in terms of wind waves, we said that the factors which which affect wind wave development are the power, of course, of the wind. How strong, how intense is the wind? How rapidly is it blowing? And as the wind blows across the water, we said initially that it builds up capillary waves, tiny waves, and that when these waves sort of extend above the level ocean surface, the frictional drag on each wave increases. And so you can think about the wind blowing over time. Gradually, the angle of the waves is going to get steeper, the waves are going to get larger, and they're going to interact more forcefully with the wind. So the power of the wind, the strength of the wind, is certainly a factor in wind wave development. But then the other factor in all this is how far across the ocean the wind is blowing. And that distance is called fetch. And so the length of the fetch is directly proportional to the size of the wave. So the length of the fetch and the strength of the wind are the two factors which allow wind waves to develop. And we talked about free waves and forced waves. So free waves are waves that are continuing, so energy is continuing to be transmitted through the ocean by these waves or with these waves, but the disturbing force, the power that's generated the waves, has is no longer forcing the waves to continue. They're simply moving on their own, with the energy that was initially imparted in their generation. And the best example of this would be the waves that would be generated if you threw a rock into a lake and you saw the ripples departing. So the energy, the disturbance which caused those waves initially has dissipated or is no longer in force, but the energy is continuing to be transmitted outward in space away from the point of disturbance. So that's one force, one kind of free wave. The other kind of free wave can occur, as we saw in that video, condition black, where a storm is blowing or has occurred and is over a long fetch, but the waves that are transmitted by that storm, by that disturbance event, are arriving at a site thousands of miles distant from the storm, which the site is not being affected by the storm. So those waves are free from the disturbance that caused them, and they're simply energy which is being transmitted along. Okay, so free waves and forced waves. And then fetch and wind power. Important concepts in this. We also talked about ocean waves, and we described waves as the orbital movement of particles of water or parcels of water or objects floating in the water as this energy passes through. So the energy can be represented as a sine wave, and the movement of the water can be represented as these little orbital circles. And the circles transmit energy downward into the water column because of the friction between the water molecules. So these upper water molecules or water parcels are orbiting, and that orbital force is transmitted to some degree to water parcels further down in the water column. But that transmission is lost, some of that is lost. And so by the time you get to about half of the wavelength depth, so a depth equal to half the wavelength, that energy is completely dissipated. So there's no longer, the water parcels are no longer set in motion by the energy passing through the surface waters. So the size of the orbit decreases with depth, and the motion ceases at half the wavelength. So critical rules of thumb. Okay, and then the other important thing we talked about was the speed of the waves. We said the speed of the waves is proportional to the wavelength and the period. Wavelength, of course, as we defined, is the distance from trough to trough, peak to peak, and the period is the number of the length of time for one from between one peak and another peak passing a fixed point. And a way to think about this, to understand how we could translate this into speed, is to think about the wavelength as being step length. What's your average step length? And then the period is the number of steps taken past a given point. So as the number of steps that you take increases, even if the wavelength doesn't, then your speed has to increase. So these are all proportional characteristics. And we can also, because of the orbital motion, characterize these in terms of gravity, the wavelength, and the orbital motion here represented by 2 pi. When we looked at the effect of waves, or the interaction of waves and land barriers, we distinguish between ocean waves, in which these orbital paths are free to decay in force as you move downward in the water column. So deep water wave is unaffected by the friction of the bottom. As long as the depth of the water is greater than or equal to 1/2 the wavelength, there's essentially no deformation of the wave due to passage over the bottom. But when the depth is less than, here in this case, 1/20th of the wavelength, then you start to see this shorter wavelength. Actually, the waves start to feel the bottom at about less than half wavelength. But when the depth really decreases, you start to get this elongation of the orbital circles, and the wave peaks have to become higher. And so wind waves can be free waves, they can be forced waves, they can be deep water waves, or they can be shallow water waves, because the length of the wavelength of typical wind waves is in the open ocean almost always less than the water depth. But longer waves that have much longer wavelengths have more interact with the bottom. So seismic waves, which have wavelengths, if you remember, seismic waves have wavelengths of up to 200 to 300 kilometers or even farther. That distance between the peaks of a seismic wave is always much greater than the water depth. And so these seismic waves are always classified as shallow water waves. And so this elongation of shallow water waves, particularly as the depth really decreases, can cause the peak of water, the height of the incoming wave, to really increase. And we'll see some examples of that in a video that I'm going to show toward the later end of the lecture. So seismic waves are always shallow water waves. Well, there's another type of wave that we're going to be introducing today, and then in your reading next week, and those are waves generated by tides. Sort of don't think of tides as being waves, but as oceanographers, that's how we have to represent that transmission of energy through the ocean body. And there's some interesting theory that goes along with describing those. But seismic waves and waves caused by tides are always shallow water waves, because they have to interact with the bottom because the wavelength is so long.
I have a question.
Yes, Damon.
Would a tidal wave also include like a tidal bore?
Okay, a tidal, you mean the wave of a tide? No, a tidal bore is a particular formation of a wave that's generated by movement of water through a shallow channel. So a tidal bore is a type of wave. It's called a standing wave, and it's generated, by the excess of water that builds up, say, down a river. So typically, you get tidal bores when the tides force a body of water through a constricted area like a river or another channel. And so you can get tidal bores that go upstream as the tide is incoming and then downstream as the tide is outgoing. So tidal bores are a wave form that's generated by interaction of these excesses of water moving in and out of an interior water body through a channel or a river, and then the interaction of that body with the shape of the channel and the shallow bottom. Okay?
Thank you.
So as the waves point to shore, half the wavelength, the wave crests become peaked, the wave starts to slow down, the wave energy is continuing to go, and the wave breaks when the water depth is less than the ratio of 3/4. And then we got to look at that great video. I like to show this video for the class because it brings in a lot of principles of waves. This is the conditioned black video that we looked at. If you had to miss class on Tuesday, you've had to look at this in order to answer the quiz. And a lot of the things that particularly the Professor Grieg talks about really explain very clearly with nice diagrams what causes breaking waves, and it describes the situation of 3 waves arriving in Hawaii in 1998, and generating this unusually high breaking surf. And you'll recall that they described, the waves that are arriving in a place where they typically were doing big wave surfing were unrideable because the waves had become so chaotic and broken by interacting with the bottom that was shallow in proportion to the length of these very large free waves that were emanating from the storm that occurred off Japan. And so, but the initial break of the wave was caused by the interaction of these long period waves that were arriving with a break called Log Cabin, which was about a 5 or 10 foot shelf, as it were, in about 50 feet water depth. And so those built up into those massive great waves that were surfed. Now, interestingly, what the surfer at the end said, well, I surfed the biggest wave and it was about 85 feet tall. I read recently that an even larger wave was surfed in Portugal by a female surfer. I think she was Brazilian, and she caught a wave that they believe was almost 100 feet high. So the record of the biggest wave ever ridden was not set or was broken subsequently several times, and most recently in I think 2019. Okay, so that's a bit of a recap over the topic that we covered, and here's a little quiz over these things. And I'm just going to throw these questions out here, and I ask for somebody to raise their hand or unmute their microphone and answer these quiz questions, just to let me know that you're out there and alive and paying attention. So question number one, the three factors that determine the size of waves are wind speed, wind duration, and A, temperature, B, pressure, C, depth, D, fetch, E, period. Who wants to answer that? Go ahead, Jacob.
That would be D, fetch, right?
D, fetch, absolutely. The size of waves of these three. Now, period does not affect the size of the waves, neither does temperature or pressure. Depth will affect the size of waves, but only in the case of breaking waves. So the basic waveform is not affected by fetch, by pressure or depth. But fetch, the length of the ocean over which the wind is blowing, is one of the three factors that determine the size of waves. Okay. Question number two. Free waves usually arrive at the shore along with an intense storm. True or false? Somebody other than Jacob. Come on, this is an easy one.
False.
Who said that?
Caroline.
All right. And you said true or false?
False.
You said false. Well, good, because that's the right answer. As we said, free waves, which are can be generated by storms. If there's a storm and the waves are coming in, the waves are still being forced by that wind, even if they're coming in from a slightly different direction, which does happen. So you can have swells and free waves arriving from some event, some distant event, but as soon as they start interacting with the present event, like an intense storm, then they're no longer free waves. They're being forced, albeit by a different set of circumstances. So free waves generally will not rise, or basically cannot arrive at the shore along with an intense storm, because the intense storm is going to force waves of its own. A breaking plunging wave occurs when A, the bottom depth decreases sharply near the shore, B, a fully developed sea encounters a new storm, that was B, C, the bottom depth decreases gradually near the shore, D, separate wave trains interact constructively, or E, because of enhanced deep water formation. So what's the answer to this? I think I just basically gave it, but Somebody help me out here. Come on, don't be shy. You just got to unmute your microphone and yell out the answer.
Is it E?
Is it E, enhanced deep water formation? Is that what you said?
Yeah.
Nope. Somebody help Mason out here. Enhanced deep water formation, that would be, you know, the cobbling effect that we get when in the North Atlantic, when North Atlantic deep water is formed. So that's kind of one of these distractor questions that sounds impressive, but it's not really the right answer. So what did I describe? What did Professor Grigg describe at Log Cabin? What was Log Cabin?
Is it A?
Is it A?
It's A, that's right. The bottom depth decreases sharply near shore. So if the depth is increasing gradually, then you do get this spilling wave. But these incredible breaking and plunging waves with these amazing curls like we saw in the video, they are a result of this abrupt change. It's sort of forcing all the water upwards suddenly in space and time and creating these really big breaks. So a surf break, which is something that all surfers want to see, that's describing a offshore shelf that causes surf to break and make the kind of waves that surfers like to ride. So when you say, oh, that's a good break there, or that beach has a good break on it, they're not talking about a break in the waves, although that is the result of the break. What the surf break actually is some shape of the bottom, some bottom formation that causes this abrupt decrease in depth, so that incoming waves of the proper wavelength interact with that barrier, and they pile up suddenly, they break and plunge, making the curl that all surfers love to see. Okay. So the last question here, waves with a wavelength of less than 2 centimeters are called something, and their restoring force is something. Okay, so is that A, ocean waves, gravity, B, capillary waves, surface tension, D, tides and the gravity of the moon, D, breaking waves and ocean depth, or C, free waves and gravity?
B, capillary waves.
B, capillary waves, little tiny waves. And so these waves, the restoring force is not actually gravity, but it's the tendency of the surface tension of the water, which is pulling the water molecules back. Okay. All right, so there was a little quiz to make sure you're all paying attention. Now we want to talk about some special characteristics of waves that produce some of the shapes. You know, like the question about the tidal bore was helpful because it's reminding us that waves are, you know, they're not these theoretical things, and they're not sort of encountering uniform conditions, but there are many variabilities created by different weather conditions, different shoreline shapes or different obstacles in the ocean, and indeed the interaction of waves that are generated from different forces that are moving in different directions and come together. So let's first think about the way in which waves are changed by interaction with the shoreline. So waves are arriving from the ocean, free waves or forced waves are being transmitted, and they're changing from ocean waves, where the molecule, the water motion is orbital down to about half the distance of the wavelength, to waves that interact. And the example that we just talked about were breaking, plunging waves, where their interaction is with a shelf break, with a surf break. But we can imagine other sorts of reactions, and one type is wave focus. And wave focus creates different forms of waves, but over time, the impact of these waves on the coastline has very marked and distinctive geological consequences for the coast, the morphology of the coastline. I wonder how many people in the class have been to the the Pacific coast well, it's the only coast in California. How many people have been to the California coast, say Point Reyes or Muir Beach or any of those places? Anybody done that? Somebody? Yes, okay. Well, 2 or 3 of you have raised your hands. So yeah, so the coast of California and the coast of the Pacific coast generally is an incredibly beautiful and picturesque coast. It has to do in part with the way in which that coastline was generated. So that coastline is generated it's a seismically active coast, and so there tends to be a more prominent and less sedimented coastline. But then that coast is interacting with waves, and what you see when you drive along Highway 1, for example, from San Francisco to Monterey, is an incredible series of embayments, and then these extended headlands, and then very often these sea stacks, which are piles of rocks that sit out in the surf. And what's happening is that over time, as the wave crests come in, the energy is and the impact of the waves is deflected and focused by these irregular barriers formed by the incoming waves. So the waves come in, the energy diverges, and so the beach between the headlands tends to be broad and shallow, broad and with low-lying area, and then the headlands tend to extend outward. And over time, as this energy comes in and is concentrated on the flanks of these headlands, some of them are cut off and eroded away, and you end up with these sea stacks, these amazing offshore rock features. I should have brought some pictures of those. I've spent a lot of happy hours traveling around in that part of the world and really appreciate that topography. But that's very much a function of the huge swells that come in from the Pacific Ocean, across thousands of miles of fetch and break on the coast out there. So there's some massive waves, and some really big wave riding does occur in Northern California, particularly in the wintertime. So that's something that happens. Okay. Let's skip past that. All right. All right, so that's the sort of interference of waves and the deformation of the waveform, dissipation of the energy in irregular ways caused by an irregular barrier, namely the coastline, and the way in which the barrier is eroded by this wave energy over thousands of years, geologic time. Now we can think of interference as happening not just by waves reaching the coastline, so that the interference is not just the barrier, the obstruction of the coastline against the incoming energy, but suppose you had waves, and this is not hard to imagine, that free waves, free ocean waves, let's call them free waves, that were generated by disturbing forces in different directions or different locations. And so these wave trains would arrive together and would interact with each other. The energy from one is going to interact with the energy from the other. Well, there are 2 types of interaction, constructive and destructive. And both of them are going to produce changes in the energy transmitted beyond the interaction zone. So constructive interference is caused when the wavelengths are at approximately the same phase. So the peaks and the troughs are approximately co-located. And when that occurs, there's an additive increase in energy. So we can think of that as, if there were waves moving along and other waves came in at approximately the same wavelength and size, then these waves would add up. The energy would be added, and you would produce, the result would be higher waves, bigger waves, longer wavelengths, and potentially increase in wave period, decrease in wave period, more rapidly moving waves. If the wavelengths are out of phase, then they cancel each other out. And so the result would be a decrease in the energy. And this can occur, according to, as the phase of the wave energy, if one set of waves is slightly ahead or slightly behind the other, you're getting constructive interference, addition, and when they're in roughly the same phase, you're getting destructive interference, subtraction. So interference of an interaction between waves in generated by different disturbing forces and arriving from different directions can cause this increase or decrease, constructive or destructive interference, and change the amount of energy being transmitted farther. So that's an example of interference. Now let's consider the interaction. Let's see. Of rogue waves. And so rogue waves are an example of constructive interference that produce very large waves. And so rogue waves are, when the sort of, not the, I don't want to say perfect storm because that's a little confusing, but the perfect, a really constructive set of circumstances arrives, and you get a very, very big wave in the middle of, smaller but still large waves. And these rogue waves can occur. They're hard to predict. They're random. They're, rare events. They're like getting a straight flush or something like that. Not very likely, but they can occur, and they produce giant ocean waves. And they can also produce very large waves on shore. So I talked about being in the Pacific coast, and one of the things that they say in the Pacific coast, and it applies everywhere, is never turn your back on the ocean. Why do they say never turn your back on the ocean? Because one of these rogue waves generated by this sort of constructive interference is always a possibility, and you could be there watching the waves break on the ocean, quite safely at some safe distance, and turn your back, and a rogue wave can come in and unexpectedly flood you. And people drown every year as a result of being careless around these large ocean waves. Okay, all right, so that's one set of interference. And let's see. All right, so I've talked about wave diffraction, or interference is a form of wave diffraction. It's also possible for waves to refract. What is refraction? Let's see, here we go. Okay. So remember what we've talked about refraction under a couple of different circumstances, and refraction is really caused by changes in the speed of waves as they move through media of different transmissivity. So if a wave is moving along the shoreline, and the end of the wave is in deep water, so it's not being affected, so the water depth is greater than half of the wavelength, the wave continues moving along. So this portion of the waves are unaffected by the shore. But as you get closer to shore, the wave is less than half of the wavelength deep. So again, imagine a series of waves that are moving parallel to the shore. And the deep water waves can move on. The energy is allowed to freely pass, and these waves do not slow down. But as the waves approach the shore and get into shallower and shallower water, they're increasingly slowed by the friction of the bottom. So the waves bend and they become more parallel to the shoreline. That makes sense. So, these waves are traveling at an acute angle to the shoreline. And then as you get closer and closer to in shallower and shallower water, those waves are refracted. They change in speed and period, and they begin to flow. Because they're slowing down, they begin to flow more or less parallel to the shoreline. And you can see that, very graphically illustrated in this picture that I found. So here you see these waves, and the waves are moving, roughly from top to bottom. So that's the offshore waves. And then there's this headland here, and this headland is interacting with the waveform. So these waves are this portion of the wave is being slowed down more than in this portion. And you can see that this, the waves where it's slowed, the waves, which we can see visualized here as the dark shadow of the wave crest, those shadows are becoming increasingly parallel to the shoreline. So the refraction of the wave energy, as that energy is slowed by the bottom and then ultimately by the shoreline, produces this change in direction. And that sort of change in direction. And you can also see, if you look here, that there's a decrease in the wavelength. If you look approximately here, you can see the wavelength distance from peak to peak is about the width of the arrow on the cursor, but that as you move closer to shore, that wavelength becomes decreased quite a bit. So the wave, the distance from the waves has decreased. Well, of course, the waves are becoming shallow water waves, and then ultimately are breaking. Okay. Well, what would happen, for example, if we combined a current with wind waves? And so let's imagine that we can get all this, we can start to make really complex pictures about here. So combining the waves and currents. So the waves are approaching the shoreline at an angle, okay? And these waves are, so here's the waves moving along the shoreline, and there's a longshore current. Okay? And so here's the surf zone, here's the half the wavelength distance, and here's the bottom contour. So out here, these are deep water waves, and in here you can see just what I was showing in the previous picture, that the wavelength is decreasing. And so these wind waves are refracting. So the waves move along on shore and then return straight down the beach. And so the result of this is that waves are moving down the coast in this zigzag pattern. Okay. Well, this sort of wave interaction is particularly notable in the Florida coastline, because we get that a lot. We get these alongshore currents and waves. And the result of that over geologic time is that beach sands and in fact entire sandy islands tend to be eroded at their heads and accreting at the downstream area. And so, barrier islands these islands, which are offshore deposits of sand and silt material, they tend to migrate along with the average direction of the waves. And so the natural condition of barrier islands is to be gradually migrating along the shoreline, along the coastline, in the direction or the average direction of the waves. Now, we have unfortunately built a lot of property on barrier islands. And so people don't want that island to migrate out from under their housing development or their vacation home. And so they do all kinds of things on the headland to stop that happening, put up big barriers and stuff like that. Well, that's only a temporary fix because the processes that are producing this migration are inexorable and continuous. And sooner or later, no matter how many big the barriers you put up, you're going to face conditions of migrating shorelines. So that's something that happens. So this longshore current produces can transport huge quantities of sand, and that's a factor that the people who are trying to maintain sandy beaches are constantly dealing with, is that their sand tends to get washed away, and they try to keep it where they want it in front of their hotel, but to no avail. And so you end up having to go get the sand from where it ended up and bring it back to where you want it to stay, which is kind of a Sisyphusian process. Okay, so that's there. You can also get wave diffraction, if by a series of islands. So this is imagining, the scale here is a little deceptive here. Imagine that these are islands, like the size of Hawaii, and that there's a very large wave train moving across. Well, as the waves interact with these island barriers, the waves that are transmitted beyond the island barriers are going to should be altered in shape. And so there can be constructive and destructive interference in these wave trains whose shape has changed by the barriers. Now, the Polynesian navigators who managed to sail across, vast stretches of the Pacific Ocean without compasses or sextants or GPS satellites or any of that, these navigators were so attuned to the shape and the direction of waves that they could identify the possibility of there being islands far, far out of sight of where they were sailing, which had produced these sorts of change. So imagine, a ship sailing in, with a sail and a bunch of people on board, and they're sailing across and they're trying to find land. Well, they come into this region here, and all of a sudden the waves change, the shape of the waves change, and they start to see this sort of wave crest reinforcement due to diffraction and interference. And they could then surmise that somewhere, if they were sailing from left to right, somewhere towards the top of the page, there must be some barrier which is causing this change, this alteration of the wave state. And so that would tell them, okay, well, we got to make a left turn here, got to turn towards the top if we want to find the island, and then they would sail. They would be able to use that observation to set a course for an island or an island chain. And that's one of many features or many observations that Polynesian navigators were able to utilize in their amazing feats of open ocean transfer. Okay, so we're gonna, I guess one last feature that I wanted to talk about, and then we're gonna move away from ocean waves and look at some waves that are occurring under different circumstances. Now, I've been saying all along that that water doesn't move as a result of waves, that only energy is being transmitted, but that is not strictly true. There's something called Stokes drift, where there's a slight mass transport, and that has to do with well, what happens is that.
Let me know if you need a hotspot, my love.
Hello? I'm sorry, did somebody have a question? Okay, just random interference. If you imagine waves that are behaving, like this with no wind, when there's an interaction of the wind and the waves, you can get a secondary wave forming at the crests of the primary wave. And so this is going to change this orbital path and give a result of a slight transport. And this transport is called Stokes drift. And so this is caused by open orbits, and it's particularly noticeable in the very surface of the ocean. So Stokes drift is something which comes into account when you're trying to track the probable movement of objects floating in the water. For example, buoys, or a lot of times when they're trying to search for somebody who's lost at sea. A boat is drifting and they're trying to track it. Oil spills, when oceanographers are trying to calculate the trajectory of oil spills, they have to take into account this slight drift, caused by this interaction of a wind with free waves to account for this motion. So, although I've said, and although you can sort of bank on it, that most of the the water remains stationary as a result of passing waves, there is a secondary effect which can cause a drift of floating objects or of objects suspended in the water. So that's called Stokes drift. Another thing that we want to talk about is something called standing waves. And the way to visualize standing waves is to think of yourself as sitting in a bathtub. Okay, so imagine this is a basin here. It's not a basin, but a bathtub. And suppose you created a disturbance at one end of your bathtub. Make it a long bathtub or a lap pool or something like that. Suppose you created a disturbance at one end of this pool, say by jumping into the bath, or running some water or something. So there's a crest at one side of the water. This concept of standing waves is going to be important when we talk about the difference between the equilibrium and the dynamic theory of tides. It's something called amphidromic points. Okay, so you create a wave, and the wave moves through here, but the wave can't continue going. This is a closed basin, right? So the maximum, so the water, is trying to orbit here, but it has to come back, and there is a node of no motion. So and that occurs theoretically in the middle of that, the center line of the basin length. So as the water flows through, comes back, the wave is moving in the opposite direction. The orbit is being completed, but the orbit is essentially around this nodal point. Okay, so a standing wave oscillates around a node, a point with no vertical motion, and you can visualize that, at least intuitively, by thinking of water sloshing back and forth in a long, deep bathtub. And okay, one other topic here is the idea of internal waves. And I think I talked about these on Tuesday, but internal waves are waves that occur within the water, not just on the surface of the water. And waves particularly noticeable at interfaces, barriers where there are two densities. And of course, the most extreme interface is the interface between air and water, and that's where you get these wind waves. And these wind waves, typically can be fairly substantial, but their wavelength is much smaller than they are in internal waves. So internal waves are occurring when there's a movement of this interface up and down as energy is transmitted through. And these waves have very, very long wavelengths. And they occur at the interface of water layers of different densities, and these water layers of different densities, we call that one of these density interfaces the picnic line. And so internal waves can move through the picnic line, and they typically have a much longer wavelengths than surface wind waves. Now, you know, if the ocean and the atmosphere were nearly the same density, these waves would continue going forever. But the fact that there are different densities means that there's a frictional impact on the transmission of this energy, and waves will eventually dissipate. Will eventually, you know, if the ocean were infinitely long, you could start a wave moving, you know, with a disturbance at one end of this infinite ocean, and that wave would not be transmitted you know, forever, because the friction of the wind and the air and the water would eventually cause that wave to dissipate. Okay, so those are internal waves, waves at density interfaces in the interior of the water column. Okay, so we've talked about waves in a bunch of different ways. Now I'm going to show you a diagram, which is a spectral diagram, and I think I've showed similar diagrams previously. This takes a little looking at, but it kind of hopefully puts everything into some kind of perspective here for you. And this is a spectrum of, this is not in the book, this is a spectrum of wave types. And this is a new sort of diagram, and we may be using some more diagrams like this. On the x-axis, we have periods. And so these are a measurement of time, and this is in exponential form. So it starts out with very long wavelengths, and then the periods get smaller and smaller from left to right. So here we have a year, 100 days, a week, a day, an hour, a minute, a second. And so these are the periods with respect to seconds. So second is 1, and then we increase in period as we go toward the y-axis. Okay. And so on the y-axis, we're seeing relative energy, how much energy is present in these waves of different types. Okay. So wind waves are and swell have periods that are between 1 and 10 seconds for the most part. So the peak occurrence, and this is sort of averaging out over all the waves that occur, the peak is between 1 and 10 seconds. And you know, with a trough in the middle here, I'm not exactly sure what causes that down dip. Oh, I guess this is these are the wind waves, and this is the swell created by wind waves. Okay, tsunamis would occur in this true tidal waves would occur in this intermeeting period, and then you have tides. And the tides have periods of 12 and a half, 24 hours. And so these are long gravity waves caused by the interaction of gravity or disturbing force of gravity interacting there. So this gives you a sense of the spectra of energy. So there's huge amounts of energy being transmitted in tides. The tides are moving massive amounts of energy or transmitting massive amounts of energy around the globe in the form of waves. But notice how tightly defined the periods are. So that's, you know, that's to say that there's a 12 and a half and 25 hour period or peak in the amount of energy that's being transmitted. So these are very tightly confined around these specific period lengths. And we start talking about tides in a few minutes here. This will probably make some more sense. Okay, so that was by way of introducing that. Okay, let's see. I think I'm going to switch to the introduction. I've got some other things that I want to talk about in terms of setches, storm surges, examples of tsunamis and great things. I think I'm going to leave those until, well, we won't do it on Tuesday because of course on Tuesday you have your midterm. But I wanted to introduce some important concepts of tides from chapter 11. And in terms of questions on the exam, they'll be limited to what I can make it through in the remaining 25 minutes or so of class. Before I go on, does anybody have any questions over the material on waves that we covered Tuesday and today? Any questions at all? All right, hearing no questions, let me switch to struggling a little bit with my okay. I want to talk, this is an introduction to the material from chapter 11, and I hope I have enough time to get through these basic concepts of the dynamic and equilibrium theory of tides and what tides generate. So tides are caused by the gravitational force of the sun and the moon, and very importantly, the fact that the earth is rotating under that force. And the wavelengths of tide is potentially half the circumference of the earth. And they are the longest waves that occur. Tides are always forced waves because the force of gravity from the moon and the sun are continuous and always acting on water. And so the planet is orbiting, and the waves are trying to, the tidal bulges are trying to keep up with that orbital motion. Okay. An important point of tides is that they are uniform forces and they exist everywhere. This will become more clear as we talk about some of the details of this. But I wanted to emphasize this, is that the tidal energy, or the energy waves, these long planetary waves that we've identified in tides, that influence is not just the surface of the ocean. It's not just what we see when the tide rises and falls on the coastline, but it's happening everywhere. And so the example that I'm giving here is, this is I deployed a CTD, conductivity, temperature, and a depth sensor. And remember, we talked about those a couple of chapters ago. And this CTD I put out in about 550 meter water depth, and I left it there for the better part of a month and came back and got it. Okay, and so while it was sitting in the bottom, it recorded, I think, just about every minute, the temperature of the water, also the salinity, but I'm not showing that in this diagram, and the pressure. Okay, well, remember that the CTD is measuring the depth in the ocean, and so it has to have a very precise pressure sensor to know how big the stack of water over the CTD is to tell what depth it's at. Okay, well, this particular instrument was sitting on the bottom, and so and it was recording its pressure at all times. Well, if you look at here, you can, this red line is the pressure. There was a slight trend in this, and I've taken that trend out. And so this is the variation in pressure on a daily basis over that roughly month-long period. There's also temperature effect going on. But let's ignore temperature for the time being. So what we're seeing here is that we start out on the 15th of August, 2003, and the pressure here, and then it goes down, and then gradually the pressure keeps coming up. Well, these peaks and troughs, these peaks have a uniform distance between them. See, there's always and that's, we can think of that as a wavelength. So these wavelengths is measured in time. The period it takes for the wave to pass between it are always about 25, they're about a day apart. They're actually about 25 hours from peak to peak. And you'll also see that during part of the phase, this amplitude of these differences is relatively large relative to other periods. Okay. We're talking about change in pressure. Let's switch over to this alternate y-axis here on the right-hand side of the screen, and this is showing the actual pressure. I've presented this pressure in something called decibars, and a decibar is equal to roughly 1 meter of pressure. And so, at the bottom, I said we were at about 550 meters of water depth. Actually, I set that a little bit wrong. The actual water depth was about 547 meters water depth. And you can see that, the pressure in, the apparent. Okay, so what is the instrument measuring? It's measuring the height of the water above the instrument. In other words, the depth of the water. And the water depth is changing. And look, it varies between between 547.9, so almost 548 meters here, down to 547.1 meters. So the maximum variation in depth here is about 0.8 meters, 80 centimeters. Okay, so that's the height of this bulge where it's moving across the Gulf of Mexico. It's got about a 1 meter maximum height. And then you have other times in here where there's almost no change in pressure from day to day or from peak to peak in this. Okay, so this is an example of how the tidal energy or the tidal force is a variation is being expressed at the bottom of the ocean as measured by a device which measures specifically the pressure of the water, and that water pressure is determined by how deep the water is at that point. Okay, so we know that the water depth didn't change in absolute terms, of the basin depth didn't change because the instrument's sitting on the bottom, but the amount of water over it is varying. All right, well, let's examine this a little bit more closely. Okay. So this is something called the equilibrium theory of tides, and we'll introduce this in a simple case here. And you remember this point of no motion. So the equilibrium theory says that at high tide here, the highest bulge in the water is being generated at the side of the Earth which is facing the moon, and this side of the planet. The planet is orbiting, of course. And then there's a bulge on the opposite side, which is creating two forces. And these opposing bulges are generated by the attractive forces. So there are two bulges, one in the direction of the moon and one in the opposite. Okay. And what are the forces acting on these? This is inertia, sometimes called centrifugal force. And this is the force that results from the fact that the planet is orbiting, sort of rotating on an axis. In this case, the axis is drawn at right angles to this point, but we know, in fact, that it's at slight offset. Okay. Well, so that's the, sort of the big picture theory. Now, why is this occurring? Well, when we think about the attraction of the gravitational attraction of the moon's gravity, or the forces that the moon's gravity is exerting on Earth, we think of the Earth being pulled towards the moon, but the moon is also being pulled towards the Earth. Okay? And in fact, it's not that the moon is orbiting the Earth in a constant way, it's actually that the Earth is being slightly orbited at the same time that the moon is orbiting. So they're actually orbiting, the moon and the Earth are actually in this sort of dance where they're both orbiting, and the center of mass is not the center of the Earth, but it's offset from the center of the Earth. So as the moon travels around, there's also a force that's being exerted on an offset force that's being exerted on the Earth. And that center of mass, you know, if we had, if the Earth had a much smaller mass, and these two things were orbiting each other, you know, this center of mass could be between the two bodies, and then both bodies would be moving in this complicated shape. It's something that occurs in astronomy when you have double star systems. And double star systems, you know, are two very large stars with massive gravitational attraction that are pulling on each other, and you get this very chaotic motion. Well, because the center of mass in the Earth-Moon system is interior to the Earth, you don't get much interaction. You know, the Earth is not being displaced as it moves around. But there is an effect here. And so, you know, one way of modeling this intuitively is to think of this as a wrench, you know, with the center of mass, you know, constant. So that, you know, and this is vastly exaggerated, of course, but it's moving like that. Okay. Well, the whole trick to this is that the planet is rotating underneath this orbital tidal bulge. And so, you know, here we are, we have the moon, and in this case, we look at the North Pole, and in fact, it's offset, and I'll show you that in a second here, but this is for purposes here, this is showing this in the same plane. So, you know, the moon is attracting here, it's high tide at midnight, the planet is orbiting in this direction from our west towards our east. And in high tide, so this is producing a high tide at midnight. And then, you know, the planet orbits 24 hours, but the moon is, you know, has in that 24-hour period that the planet is orbited, the moon has progressed in its orbital path around the Earth. So relative to the moon, or, you know, the relative motion of these systems has a period not of 24 hours, but of 24 hours and 50 minutes. And that extra 50 minutes is generated by the fact that the orbital path of the moon follows the rotational axis, or the rotational path of the planet. Okay, so that's saying that if we have a high tide at midnight on day one, on day two, the high tide, the time at which the bulge is going to be facing toward the moon or away from the moon, that's going to progress in time to 12 hours and 50 minutes, midnight plus 50 minutes. So 050, you know, 050 in the morning. Okay. All right. So that's one factor that causes some discrepancies in that period. And something to note here is that, you know, we have the moon, you know, we know that there's one side of the moon that we see, and then there's the dark side of the moon, the side of the moon that is never facing towards Earth. And that's because the moon has become tidally locked. Its tendency to orbit, and it probably did begin, you know, when the moon first formed, it probably did rotate on its axis, but that rotational energy was slowed over time until the moon became tidally locked with the Earth. In fact, I talked about the Earth exerting a force on the moon. Well, that force is also being exerted on Earth, and Earth's rotation is slowing gradually as a result, very, very gradually, as a result of energy dissipated in this system. And also the orbital distance from the between the Earth and the Moon is gradually decreasing over time. These are not differences that you would notice if you're traveling on a spaceship from Earth to the Moon, but it is measurable astronomically. Okay, so that's one effect, and we're in this we're looking down in this from the top of the orbital plane. But if we take a side view of this, we have to remember that the moon's orbit is displaced. So the moon is not orbiting with respect to the north and south, the rotational axis of Earth's location. The moon is at an angle to that. And so that angle is like this. So that's going to produce, a difference in the bulge from north to south. So the orbital plane of the moon is tilted with respect to the Earth's axis of rotation. So, we can sort of imagine that. So this island is exposed at low tide, submerged at higher tide, as this orbital bulge moves around. Okay. So what that's showing is that this bulge is not displaced evenly by latitude. So this island is at a constant latitude, but the bulge of the moon, or the bulge of the high water created by tide, the tidal attraction of the moon, is going to vary from north to south. And here is a theory of that. Okay, so this is just another way of looking at this same period to sort of recall that the attraction toward the moon is offset from the axis of Earth's rotation. All right, so we're talking about how the gravitational attraction of the moon causes this tidal bulge. Well, the moon is not the only body, the only gravitational force being exerted on the Earth. The other major gravitational force which is exerted on the Earth is the force which keeps the Earth in constant orbit around the sun. And so, the Earth is very much enthralled to sun's gravity, but gravity increases as a cube of distance. And so the Earth being so much closer, the moon being so much closer to the Earth than the sun, its gravitational influence is much greater on the water, on the tides. But the two forces do act together. Okay, so there's a solar tide and there's a lunar tide. Okay. Well, the moon is orbiting the Earth, and the Earth is orbiting the sun, of course. And then here are so when the sun and the moon are lined up, and they line up when there's a full moon and a new moon. Okay, so full moon is when we see, the fully illuminated disk of the moon, and the new moon is when the dark of the moon, when the moon is completely in shadow, or we see the shadow side of the moon, because the illuminated side of the moon is facing towards the sun, and we're seeing the side that's away from that. Okay, so that implies that at one time during different times during the orbital cycles of the sun and the moon, we're going to have an especially high tide. And then when the moon is at right angles to the sun, the attraction of the sun, then there's going to be a relatively low tide. Okay, so you can think of this as destructive interference between these, constructive and destructive interference between these two waves generated by the attraction of the sun and the moon. Okay, so this monthly, or it's monthly in terms of the lunar month, and the lunar month is not is 28 days and a few hours, and so this and that's the orbit of the moon is different from the orbit of the sun, so that's going to say that at regular intervals, as the moon completes its orbit around into and out of the maximum gravitational force of the sun, we're going to have high tides and low tides. And go all the way back to that diagram that I showed you at the beginning. So where do you think the moon and the sun were lined up? Right in here. Okay. And where were they at opposite angles? They were right in here. So over the monthly variation in tidal height, there are going to be periods of highest tidal range. Difference between high tide and low tide is going to be greatest when the sun and the moon are lined up, and they're going to be increasingly greater as these two bodies come in alignment with each other. And then they're going to decay to near zero when they're at right angles to each other. Okay? And there's bunches of variations that we can see here. Elliptical path, the distance between the Earth and the sun, which of course is changing as the Earth completes its elliptical orbit around the sun. And of course, the orbit of the moon is elliptical. So there's lots of variabilities in here. And so that's one of the reasons why you can have these particularly high tides or particularly low tides in the course of a year, because of the way in which these alignments come into force with respect to the period here. So these variables are there, and you're not going to be required for this course to sort of calculate when when these things different tides would occur. But you can see, I hope, from this illustration, the way in which these calculations would be made. The nice thing about astronomy and the movement of heavenly bodies is that within a range of known forcing factors, they're very, very predictable. So we can know with great precision, by looking ahead or looking backward in time, and knowing as we know, this great sort of celestial clock unwinding, when we're going to have high tides and low tides. So you can look in a table, and it will tell you with perfect accuracy, or near perfect accuracy, when the high tide is going to occur on a particular date, 15 years from now. That is something which is knowable, and in fact, you can look it up. Okay, so that is, now I wanted to introduce, so that's the equilibrium theory of tides. I want to just introduce one complexity in this, and then we'll think about that. So so I've been describing these tidal bulges and the way that the bulge changes, and depending if the sun and the moon are lined up together, that we would have different tidal factors, different ranges. But in fact, that equilibrium theory, which was proposed by Newton originally. So Newton was the first person, Isaac Newton was the first person to come up with this understanding that these gravitational forces would cause these bulges in water. And so he quite confidently predicted that. But he understood that, as powerful as they are, they really only account for a fraction of the observable tidal range that we have at any point. Okay? So this equilibrium theory of tides, as a result of tidal interaction, only accounts for a fraction of the total tidal range that we can observe at any location. Well, what accounts for the rest of it? And there's more stuff here I'll talk about the different types of tides. So let's see. There are, this is just sort of a cycle here showing the different ranges here. And there are tides which can occur. There's sort of a diurnal tide, which is a tide that varies with approximately a 24-hour period. And there's a semi-diurnal tide. And whether you have a diurnal tide or a semi-diurnal tide depends on where you are in the planetary structure. Okay, so this equilibrium theory only accounts for about about 25% of the total range that we can occur. What causes the rest? All right, I'm going to try to draw some pictures here to illustrate that. Now I've got just a little bit of time left, and so I'll introduce this concept here. And to the right screen. There we go. Okay. So let's imagine, that we've got a basin. Come on. No, it's right. So let's imagine that we have a basin, long basin. And in this basin, we have a wave. All right. So this is a complete wave, a peak and a trough. And, one way to think about this basin is that it's a basin that wraps all around the Earth. So on one side, there's a peak, and on, halfway around, there's a trough, and on the other side, there's another peak. So this is this is the basin. Now, and so the wave is moving in this direction, and then the wave, because it's a bounded box like that long bathtub that I asked you to imagine previously, at some period later the bulge is going to be going in the opposite direction. So this wave will later be like this. Okay. So, in this case, the water is moving in this direction, and in this case, the bulge is moving in that direction. Okay, so if we imagine, so that's looking at this from the side. If we look at it looking down, so when on this diagram, the vectors of water motion are going to be uniform in this direction. All right. And then 12 hours later, they're going to come back in the opposite direction. But the point is that from edge to edge in these basins, the movement of water is relatively uniform. Right? Well, that's sort of an equilibrium theory of water motion in this basin, which we call the world ocean. But of course, the basin is not uniform like this. In fact, there are these massive barriers we call continents. And continents are the largest scale barriers, but of course water is flowing past all kinds of other smaller barriers as well. Just to get the concept down, let's imagine that we introduce a barrier in the middle of this basin. So here's an impermeable barrier. So water cannot flow through this barrier. All right, in this condition, this is sort of, one half of the cycle, and here's the second half of the cycle. During this half of the cycle, the vectors of water motion are going to be shortened because water can't flow past. Right? Get a little bit longer, a little bit longer, and then here, like that. Okay. All right, if this is the motion of water over time, where is the water going to be deepest at this period? Well, it's going to be deepest here, where most of the water is built up, not quite so deep here, not quite so deep here, not quite so deep here, shallower here, and then across here, pretty constant, all right? So that is a dynamic effect of a barrier to the motion, this tidally generated motion of water around the planet. And that dynamic effect is the way in which tides are actually experienced, the way in which these gravitational forces are actually experienced in the present day world with the tides as we have them. Okay? And so the consequence of that, let's see, go back. Okay, so the lunar day, 20 hours, 50 minutes long. Lunar cycle is 29.51 days because it completes an orbit. These are not evenly divided. Okay. And the dynamic theory of tide explains ocean tides based on the sun and moon, so that fixed sort of clock-like motion, this should be the. And then this interaction of these basic forces with the barriers of continents. And very importantly, sort of, as you create these different barriers and different flow pathways, just like we talked about in that nodal variation, there are places in the ocean where there is no tidal variation because of the way that water is flowing past these. And these are called amphidromic points. And there are global amphidromic points in the different oceans. There's one in the center of the Atlantic Ocean. There are several in the Pacific Ocean. There's one in the Indian Ocean. And so these are points of no tidal motion. So if I had put my CTD right here at the bottom of the ocean, throughout the whole period of that month-long deployment, you would not have been able to measure any change in water height because there would have been no motion past that point. And so these global amphidromic points are caused by the dynamic interaction of this tidal bulge on both sides of the planet, or with the barriers imposed by continents and the convoluted path that water flows around it. Okay, I'm going to stop there. Just gone slightly over time, I guess. And we'll have our exam on Tuesday. It will cover all the material that I've talked about until now. And I hope you all have a good weekend and can study effectively and get ready for the exam. If you complete, the multiple choice questions and the questions that the essay questions that I put on the exam, you'll be in great shape if you understand the reason for the correct answers and how to express the questions, the essay questions that I laid out there. If you can, make that thinking part of your head, part of your knowledge going forward, you'll do just fine on this exam. So please don't be too nervous about what's coming. I'm sure you'll do well, and I'm sure you have a chance to prepare yourself for the exam on Tuesday. Okay, that's all I had. Time for any questions.
So this won't be on the exam, right?
Everything that I've covered in lecture today will be on the exam, up until the global amphidromic points.
Okay, thank you.
Any other questions?
Will the in-class portion just be multiple choice, or will it also have like short answer essay?
It will be multiple choice and short answer essays or diagramming questions.
Okay, thank you.
It's the most of the points, well, I think it's like 60-40 or 70-30 in terms of the amount of points from the multiple choice versus the short answers. Okay. All right, everybody. Bye now.